quick question before we start. If the derivative of a product were just the product of the derivatives, would that actually be true? Let's find out using nothing more than a picture of a growing rectangle. Here is our rectangle. One side has length f of x, the other side has length g of x, so the area of the rectangle is f of x times g of x. In 2 dimensions, picture the rectangle sitting flat on the page. In 3 dimensions, picture it as a flat panel tilted slightly in space, so you can see its 2 edges clearly. One edge length f of x, the other edge length g of x, with all labels kept flat and horizontal so they stay readable. Now let both sides grow a little. The side f of x grows by a small amount, call it h, and the side g of x also grows because it depends on x too. So the new rectangle has sides f of x plus h and g of x plus h. The extra area we've added is not one simple piece. It splits into 3 pieces, a thin strip along the top, a thin strip along the side, and a tiny corner rectangle where the 2 strips overlap. Look at both views again. The flat 2-dimensional rectangle with the 2 shaded strips and the tiny corner piece, and the tilted 3-dimensional version, showing the same 3 pieces stacked as thin slabs, with all text still flat and horizontal. As h gets smaller, notice the corner piece shrinks away much faster than the strips do. Before we reveal the algebra, pause for a moment and think, using only the picture. What do you think the area of the top strip corresponds to, and what does the side strip correspond to in terms of fg and their derivatives? Let's now derive this properly from first principles. The derivative of f of x times g of x is, by definition, the limit as h goes to 0 of the quantity f of x plus h times g of x plus h minus f of x times g of x, all divided by h. The numerator is exactly the total extra area we just drew, the 2 strips plus the vanishing corner. To split it apart, we use the add and subtract trick. We insert the same term, f of x times g of x plus h, once with a plus sign and once with a minus sign, so the numerator becomes f of x plus h times g of x plus h minus f of x times g of x plus h plus f of x times g of x plus h minus f of x times g of x. Now group these 4 terms into 2 pairs. The first pair is the quantity f of x plus h minus f of x times g of x plus h. The second pair is f of x times the quantity g of x plus h minus g of x. Divide every term by h and split the single limit into 2 separate limits. We get the limit, as h goes to 0, of the quantity f of x plus h minus f of x, all divided by h, times g of x plus h plus f of x, times the limit, as h goes to 0, of the quantity g of x plus h minus g of x, all divided by h. Now just recognize each piece. The first limit, the quantity, f of x plus h minus f of x, all divided by h, is exactly the definition of f prime of x, and as h goes to 0, g of x plus h simply becomes g of x. The second limit, the quantity, g of x plus h minus g of x, all divided by h, is exactly the definition of g prime of x. Putting it together, we arrive at the derivative of f of x times g of x equals f prime of x times g of x plus f of x times g prime of x. This is the product rule. Notice this is not the product of the derivatives, so our opening instinct was wrong, and now we know exactly why. There are 2 strips, not 1. Let's match this back to the picture. The first term, f prime of x times g of x, is the thin strip along the side, the small growth in f, stretched across the full height g of x. The second term, f of x times g prime of x, is the thin strip along the top, the full width f of x, stretched by the small growth in g. The tiny corner, which involved h times another small change, vanished in the limit, which is exactly why it never appears in the final formula. If this picture finally made the product rule click, hit like and subscribe for more visual maths. Next time we tackle the chain rule, and yes, we'll draw a picture for that one too.